Okay, first chapter, BIO 171, Nature's Biology, General Biology 2. I'm going to start by kind of showing you a little bit about how the video system works. You'll notice that I'm fairly well lit, and this is really overlit. Is that the video system picks something to focus on, but also something to put into the best image. And typically it looks for faces. And so what you'll see me do occasionally, especially you'll see this get much brighter than it should get, is you'll see me walk up to the screen. Now what you can't see, because my hands got to go to the screen, which is over on that side, and the camera's over here, is I just tap the screen and the video system goes, oh, you want me to look at that? And the screen becomes much more readable, much more visible. Now sometimes I'll have a cartoon up and the words are going to be pretty kind of small. And in cases like that, I will read the caption off, which I'll do right now. And it says, sure, we're dealing with tiny particles, but your formula is just a symbolic representation. Writing really tiny on the blackboard. Anyway, this is little bits and pieces version of biology, atoms and molecules and cells. And so we're going to start with atoms and molecules. This is second semester, so most of you, if not all of you, have had chemistry already. So a lot of what I'm about to go through is going to be review. There's a good chance that you may get a perspective from me that you don't necessarily get in chemistry, and some people find that useful, and some people find that confusing. Welcome to science. Atoms, teeny tiny little things that are the very smallest part of an element that you can get to and still have that element. You can take an atom of iron and break it into smaller pieces, but it's not iron anymore. You can take an atom of oxygen and break it into tinier pieces, but it's not oxygen anymore. And there's a core, the nucleus, with some particles in it. And then there's these levels of tiny little things zipping around that tend to fall into semi-discrete layers. Quantum mechanics at this level gets very bizarre, and everything that you get here is a representation of a reality that even the best people who work with this don't completely understand what's going on, because this is the smallest part of matter, the smallest bits of matter, and yet under some circumstances it behaves like it's just energy. Is that Bose-Einstein condensates do some very bizarre things where they take on wave functions and do all sorts of weird things. And I don't really understand it. I keep up with as much reading in other sciences as I can. But the way this stuff behaves on a quantum level, the atomic level, just kind of defies all acceptance of what you see in the real world. And getting those two, the real world levels and the quantum levels, to kind of mesh in a predictable, describable way is still something that physics is still trying to do. Anyway, the core is the nucleus, which is from a Latin word for kernel. And as people discovered stuff through the centuries, when there was something, a little kernel of something in the middle, they would call it a nucleus. So atoms have a nucleus, nuclei, plural, Latin. And cells have a nucleus. It's just the thing in the middle. There's no other relationship between an atomic nucleus and a cell nucleus other than they're the thing in the middle that people named using the Latin word for the thing in the middle, really. Now, as far as the thing in the middle is concerned, it has very, very little impact on biology. Is those things going around the outside have a huge effect on biology. The things in the middle we're going to talk about because it has some impact in some cases, but mostly we're going to talk about them, and then you'll notice they don't really come up again. except under very, very particular circumstances. Two different types of particles in the nucleus. So I'm going to start writing my overhead notes. I'm assuming you're taking notes, because my overhead notes, if you've looked at my notes that I post, very, very brief, doesn't say much, just reminds me of what I want to talk about. But it is an outline of the material that we're covering, so it can, some people will find it useful. What I've got up on the overhead is going to be a similar outline, maybe a little bit more detail. But again, if you're going to need to look at this later to answer a question, you need those notes to make sense to you, to have the information level that you need in order for you to be able to answer a question from them. And everybody is different as to just how much you need to write down in order to remember what it is you were listening to and watching at the time that you were taking the notes. Some people write voluminously. They write down as much as they can of everything that I say. And some people learn over time how much of what I'm saying is important to have down beyond just the stuff you're copying off of the overhead. Now, I do use an overhead projector. I'm an old guy. I've been doing it for a while. But I prefer it to PowerPoint. I don't like the way the PowerPoint makes your mind work, where it's all up there all at once. And you kind of have looked it over, and by the time I'm halfway through it, your mind has kind of wandered off because you've seen the rest of it and you kind of know where I'm going. As teachers, we tend to be a little bit too literal with the PowerPoints in a lot of cases, where it goes, he's just talking about what's up on the screen. I will write stuff down. I do believe that people that are tactile learners, that's the process of watching somebody write can actually help impact their learning situation. If you're visual, you're seeing the words. And if you're auditory, you're hearing the words. So you're getting all three levels. But typically, you don't get the tactile level. Also, I write and then I talk. So I write, the overhead projector's over there. I go and I write something. I come back here and I talk. And that slows me down. If I were doing PowerPoints, I'd be zipping through a lot faster. You don't want me to be zipping through a lot faster. Yes, these videos are going to be kind of long, but so would the lectures be. You're getting close to what the lectures would be under normal circumstances. I wouldn't be able to answer questions, but I'll tell you a secret. People don't ask questions a lot in lectures anyway. You can always send me an email question, and I will address it. If it's a question that I may address it and just send a notice to everybody. Okay, there's some confusion on this point. I won't talk about you by name. Some confusion on this point. Here's what I meant. Every once in a while, I'll say something, and I don't know I said it, and it turns out to be the exact opposite of what I meant to say. And that's one thing I don't get with a class full of people, is somebody goes, did you mean, positive, and you just said negative? I said, I did? You run that little rewind thing, so, oh, yeah, I guess I meant positive. So, this is all setting up. A lot of you know this already. You've already seen my lectures, but no, I don't have COVID. It's just a very dry winter morning. Atoms. First chapter, chapter 1:1. One of the particles inside the nucleus is called a proton. It has a few features. Each proton has a single positive charge. That turns out to be very important for a number of reasons. Each proton when people started to figure out how this works, they started to figure out how much these tiny things weighed, how much mass they had. I know they're not exactly equivalent, but for our purposes, I'm going to say weight when I mean mass and say mass when I mean weight sometimes, and probably do this little song and dance whenever I do that. But anyway, the tiny fractionation of normal measures of weight and mass just seemed eventually just dumb to try to apply to this stuff when you're discussing all of the parameters. So they said, why don't we just come up with a unit of mass that we can apply to on the atomic level? Now, we've got these particles, these kind of universal, always the same particles. And why don't we start our measurement by giving them 1 unit? A proton has 1 unit of mass. Okay. Eventually, they discovered that what makes an element is how many protons are in there. Every element has its own unique number of protons in the nucleus. And it gave them a way of assigning structure to all of the elements. So they have an atomic number. Okay, this happens sometimes when you get old. We haven't gotten really to the, I know you know, guys know what the periodic table is yet, but I'm not ready to throw one up there. But if you look at a periodic table, every single element has its own atomic number. Well, that number is also the number of protons in the nucleus. You change the number of protons, you change the element. There are processes that change the number of protons, and it shifts an element, and it makes it another element. And we will talk about that a little bit later. Also, in the nucleus are neutrons. Neutrons are structurally built up of a positive particle and a negative particle. And when you put the two together, they don't have any charge on their own. There are circumstances where they break apart, and what you get is a proton and an electron. The proton is the positive charge, the electron is the negative charge. This is beta radiation. I'll talk about that in a little bit. And the electron shoots out of the nucleus, which is a little odd considering the nucleus is full of these positively charged things. You think it would stick there, but it doesn't. It comes shooting out. And what used to be a neutron left behind inside is now a proton. And that's one of the ways you change the element. The element is now moved one spot up the atomic number table because you now have one more proton in there that didn't used to be in there. Now, I have to admit, I'm confused in terms of what neutrons are. I have learned under other circumstances, you go, well, if you can break a proton up, what's it supposed to have in it? And it's supposed to have a neutron and a positron. And then the neutron's supposed to have a proton in it. So a proton's got a neutron in it, but a neutron's got a proton in it. It gets very, very confusing. A neutron has a proton in it and an electron, but it still is represented as 1 unit of atomic mass. For a very, very long time, it was thought that electrons just didn't have any mass, that they were essentially a type of energy particle. And then they eventually discovered that it had a teeny little bit of mass. If you look it up, it's 0.00, I don't remember the number. It's a little tiny thing. So it's that they decided it was negligible. So the fact that this plus a negligible amount of mass from the electron still, we'll make it a unit anyway. Which if you know physics, you know that's kind of insane because they get nuts about precision. But, so you got 1 unit of atomic mass. I'm going to move this up. So the mass of an atom, since the electrons don't weigh enough to count it, even if there's a bunch of them, the protons and the neutrons together give you the mass of the atom, the atomic mass, the atomic weight of the atom itself, the atomic weight of the element, sort of. What are they doing in there? You get a bunch of positive charged particles stuck into a tiny little room. Now you know from other science that like charges repel each other. A bunch of positive charges should be repulsive. They shouldn't want to stay together in a little tiny room, especially since they're not confined there. They have to be held there. Now there are some forces at work inside the nucleus that help hold it together. But part of what makes a nucleus stable is the mix of neutrons that are in there with the protons, which means that there's a number of neutrons that gives you a nice stable nucleus. Sometimes there's no number of protons that gives you a nice stable nucleus, that you get more and less stable, but virtually any mixture is a little bit unstable. And then there are mixes that are much more unstable. That means you don't always have the same number of neutrons inside an atom. Well, I'm going to move this because I'm going to get into something else anyway. You got the elements, got so many protons in it. How many neutrons do you have? Well, it depends. Is that there's often a few different possible answers to that. What does that do? Well, it changes the weight of the atom, it changes the mass of the atom, but a lot of times it also is a reflection of the stability of the nucleus. Isotopes are different versions of the same atom with different numbers of neutrons in them. And almost always, the different numbers of neutrons gives you different nuclear stability. What happens if a nucleus is unstable? It will get more stable by dumping stuff off. There's a few different ways that it does this. I'm going to write this and then talk about it. I'm going to work my way backwards. Sometimes to get more stable, it just needs to release some energy. Too much going on in there, let some energy out, everything kind of settles a little bit. That is gamma radiation. That's pretty potent energy coming out of the nucleus. But it doesn't change, what it leaves behind is still the same number of protons, the same number of neutrons. If neutrons break down, an electron comes shooting out, that's your beta radiation. That changes what's left in the nucleus because you now have a proton that wasn't there before, well, it was there inside a neutron. And so now you've changed the atomic number, you've changed the element. Sometimes a big chunk comes out, a chunk that takes 2 protons and 2 neutrons with it. It's what they call a helium nucleus or alpha radiation. These different forms of radiation present different dangers when they hit biological material. Alpha radiation packs a pretty decent punch because it's a chunk, but it doesn't get very far into biological material before it hits something, so it has very little penetrating power. So alpha emitters are things that like you don't want to inhale them because they'll mess with the linings of your lungs. They can give you skin cancer, but they don't have huge, they're not going to get into your bones or anything like that. Beta radiation, tiny little particles going very fast, packed, but not a lot of mass to them. But they are electrons, so they can mess with things. They can get farther into biological material and have effects from both being introduced electrons and the fact that they get in there and hit things. And then gamma radiation is radiation with enough power that if it hits the wrong levels of electrons and other atoms, it can shake them up and spit electrons out of there. It's what's called an ionizing radiation. So those are the things inside the nucleus. And except for carbon dating, I don't know, and at the very end of the semester when we talk about some different types of analysis of things like proteins, we're not really going to talk about the nucleus much again. We're going to talk mostly about the chemistry, and the chemistry has to do with the electrons, and that's in the next video.